Hello everyone, welcome to the 18th video of our lecture series. So in this video we are going to solve some problems based on time independent time independent degenerate perturbation theory. So let us proceed with our first problem. So here we have a system with an unperturbed Hamiltonian H0 and this system is subject to a perturbation H1. So this is our unperturbed Hamiltonian and this is our perturbation. So first we have to find the eigenstates of the unperturbed Hamiltonian as well as the exact eigenvalues of the total Hamiltonian. So let us proceed. So we have our unperturbed Hamiltonian, which is given by this E0 15 0 0. So let us write down. So we have to find the eigenstates of this Hamiltonian. So as we can clearly see that this Hamiltonian is already diagonalized. So already diagonalized. So what are these eigenvalues? So H0 has eigenvalues. One is 15 E0, which is non-degenerate, and H0 has eigenvalues. One is 3 E0. So this 3 E0, as you can clearly see, that it is threefold degenerate. So we have to find the eigenvector for corresponding to this eigenvalue. So let us find for lambda 15 E0. So for eigenvalue 15 E0, so let us proceed. So here we have 15 E0. So let us suppose that the eigenvector is A, B, C, D. So for that we have our eigenvalue 15 E0, A, B, C, D. So what will be our equations? So we have 15 E0A equal to 15 E0A, and we have other equations are 3 E0B. This should be equal to 15 E0B. So this is only possible when we have B0. So from the third row we have case this. So this is only possible for C0, and similarly from the last row we can conclude that D should be 0. So we have B, C, D, all of them to be 0, and A can be any value. But we also know that our eigenstates, they should be normalized. So that means our A squared summation of this should be 1. So from that we have to have our A values to be plus minus 1. So we can choose any one of them. So we are choosing just 1. So our first eigenstate is 1 0 0 0. So this is for eigenvalue 15 E0. Now let us calculate our state or eigenvector for eigenvalue 3 E0. So for 3 E0, we have our Hamiltonian. And here we have our eigenvector. So this should be equal to 3E0 A, B, C, D. So for that, what are the conditions? So from the first condition, we can again say that this should be equal to 3E0A. That means A should be 0. From the second condition, we can say that 3E0B. This should be equal to 3E0B. So B can take any value. From the third row, we can also see that C also can take any value. And from the fourth one, we are getting this. So here D also can take any value. So and also we have to ensure that this should be 1. So what are our possible what are the possible values and simple values we can take? First, we need to know two conditions, that this eigenvectors, they are normalized and also they are orthogonal. So from orthogonal condition, if we so suppose we take these three set of values. So we are taking B1, C, D to be 0, B is 0, C is 1 and D 0, and we are taking another set, B, C both should be 0 and D should be 1. So if we take these three values, then we can clearly see that our orthogonality condition and our normality condition, normalized, both are satisfied. So if we take eigenstates, so since this is threefold degenerate, so we have to construct three eigenvectors. So if we have these three eigenvectors, one is 0 1 0 0, another one is 0 0 1 0, and another one is 0 0 0 1, then we can clearly see that these three are orthonormal. So our eigenstates corresponding to the eigenvalue 3E0 are 0 1 0 0, so this is our eigenvectors for this is our one set of eigenvectors for this Hamiltonian, which has eigenvalues of 15E0 and 3E0, among which 15E0 is non-degenerate and 3E0 has threefold degeneracy. So we found out the eigenstates corresponding to the unperturbed Hamiltonian. Now we have to find the exact eigenvalues of the total Hamiltonian. That means H0 plus HP. So what is our H1 or the perturbative Hamiltonian? So this one. So our total Hamiltonian is H0 plus H1. So where we have H0 to be E0 15 0 0 and we have our H1 to be E0 by 100 0 0 1 0 0 1 0 0 and 0 0 0 0. So this is our total Hamiltonian. So for now, for convenient, let us write we have lambda to be 1 by 100. We are just writing this lambda for keep track of what we have done before. So our total Hamiltonian will be 15E0 0 0, and here we have 0 3E0, and here we have this will be lambda E0. This will be lambda E0. So 3E0 0, and here we have 3E0. So this is our total Hamiltonian, where lambda is the lambda is for keep track of the perturbation. So where it is given as 1 by 100. Now we have to find the eigenvalues of this Hamiltonian. So for eigenvalues, so let us suppose that the eigenvalues are P. So if P is our eigenvalue, then the characteristic equation or the secular equation from which we can find the eigenvalues will be 15E0 minus P 0 0 0 0. Here we have 3E0 minus P, and here we have lambda E0 0. And here we have 3E0 minus P, and in the last row we have 3E0 minus P. So this is the equation or the secular equation or characteristic equation which we have to solve. So what will be the, so from here we are getting that 15E0 minus P. So for, and we have also 3E0 minus P, and here we will have 3E0 minus P squared, and we will have minus lambda squared E0 squared. Yeah. So if we solve this equation, so one value we have P to be 15E0. From here we are getting P to be 3E0, and from this equation we will get 3E0 minus P, which will be equal to plus minus lambda E0. So P is 3E0 plus minus lambda E0. So what are the exact eigenvalues? So exact eigenvalues of the total Hamiltonian are 15E0, 3E0 and 3E0 plus minus E0. So lambda is 1 by 100. So these are our exact eigenvalues. So now we have to find the eigenenergies of H to first order perturbation, and we have to compare them with the exact values that we obtained in A. So let us proceed. So we have to calculate the energy eigenvalues of H0 to first order perturbation. We have to take use of both degenerate and non-degenerate perturbation theory, because we have one eigenvalue 15E0 which is non-degenerate, and we have another eigenvalue 3E0 which is three-pole degenerate. So let us first focus on this non-degenerate case. So for non-degenerate case, for 15E0, what will be our eigenvalue of for the perturbative Hamiltonian? So for the perturbative Hamiltonian, the energy correction will be, if we denote this by E dash, then that will be phi 1 H1 phi 1. So it will be 1 0 0 0, and here we have 0 and we have another state 5 which is 1 0 0 0. So we have to calculate the value. So this will be 1 0 0, and from this we will get 0, and from the second term we will also get 0. From the third term we will also get 0. From the last one we will also get 0. So it will be 0. So for the eigenvalue 15 is 0. If we apply the perturbation H1, then our eigenvalue will still be 15 is 0, and in like what we have obtained in our exact case. So this is identical. And now we will focus on our degenerate case. So for degenerate case, we have to diagonalize the matrix. So this is V11, V12. I will write in a second what are this. So 2 1 1, 3 1, 3 2, 3 3. So what are these elements? So basically Vij, this is phi I H 1 phi j. So where I and j, they run from 2 to 4. Because our first state is non-degenerate, so we are not including here. Our second, third, and fourth state, they are degenerate, so we are including here this to calculate our degenerate perturbation theory. So let us first calculate V11. So V1, so 11, so here it should be I plus 1 and j plus 1, and ij they run from 1 to 3. Because for V11 we need to calculate this term phi 2 H1 phi 2. We have to find this. So let us proceed. So we have phi 2 this. We have our H1 to be 0 0. And this is our phi 2. So from that we will get all zeros and our value will be 0. So V11 is 0. Now proceed with V12. So V12 means phi 2 H1 phi 3. So what is our phi 2? Phi 2 is 0 1 0 0. Our H1 is, this is 0. And we have our phi 3, which is 0 0 1 0. So if we do the calculation, we will get 0 1 0 0, and here we will get, so first term will be 0, and for the second one we will get lambda is 0, and rest will be 0. So from here we will get lambda e 0. And our V13, if we calculate, so it will be phi 2 H1 phi 4. So it will be 0 1 0 0. And we have our phi 4 to be this. So if we calculate this, so it will also turn out to be 0. So similarly, in the similar fashion, we can calculate all other values. Like, so suppose we are calculating V21, so it will be phi 3 HP phi 2. If we do the calculation, it will turn out to be lambda is 0. Similarly, V22, that means phi 3 HP phi 3, it will turn out to be 0. V23, it is phi 3 HP phi 4, it will turn out to be 0. V31 phi 4 HP phi 2, so it will also turn out to be 0. You have to just do the simple matrix multiplication, nothing else. So V32 is phi 4 HP phi 3, which is 0, and V33 will be phi 4 H, so this is H1, these are, it is basically the perturbative Hamiltonian. So we have here phi 4, which will also be 0. So our what is our V matrix? So we have our V matrix to be 0, lambda E 0, 0, lambda E 0, 0, 0, and here we have all three terms to be 0. So we have to diagonalize this matrix now. So if we diagonalize this now, so if P is our eigenvalue, then our corresponding secular or determinant will be minus P, lambda E 0, 0, lambda E 0, minus P 0, 0, 0, minus P. So this is the equation which we have to solve. So if we proceed, so we have minus P here, we have P square minus 0, and in the second term we have lambda E 0. So for that we will get minus lambda E 0 P, this. So we are getting, like here we have P cube minus P cube, and here we have lambda square E 0 square P. So if we take P common, then we have P multiplied with P square minus lambda E 0 square. So what are the values of P? So P have values to be 0 plus minus lambda E 0. So what is our, so this will lead to the correction. So what is our correction in the first order of the second state? So this is 0, and similarly correction in the third state up to first order will be lambda E 0, and correction in the fourth state up to first order will be minus lambda E 0. So the energy eigenvalues to first order degenerate perturbation so they are E2, E2 is our E20 plus E21, that means 3E0, and we have our E3 to be E30 plus E31, which is 3. So we can write 3 plus 1 by 100 E0, and E4 to be E40 plus E41. So this is 3 minus 3E0 minus E0 by 100. So if we observe carefully, so from here also we got these values, 15E0, 3E0, and 3E0 plus minus 100. Here we are getting also 15E0, one is 3E0 and another one is 3 plus minus 100 by E0. So these are identical. These are identical with the exact eigenenergies that we obtained in A. So that is it for our first problem. So we will move with our second problem. Okay, so let us now move to the second problem of today's video and last problem. So in this problem we have to find the exact energies and wave function of the ground state and first excited state, we have to also specify their degeneracies for an infinite cubic potential well. So we have a potential which is infinite and cubic, so it is in all three direction, and it is 0 in the range 0 to L and infinite otherwise. So after that we are adding the following perturbation. So this is our perturbation, this is a perturbative Hamiltonian, and for that, using first order degenerate perturbation theory, we have to calculate the energy of the first excited state. So let us proceed. So we know that the energy and wave function for an infinite cubic potential well of size L is given by the following. So the energy and wave function for an infinite cubic potential well of size L is given by E. So basically nx, so we have three quantum numbers here since it is cubic, and the energy value is given by pi square h cut square 2m L square, and we have here nx square plus ny square plus nz square. And what is the wave function corresponding to that? So the wave function is phi nx ny nz, and it is a function of xyz, and this is given by root under 8 by L cube sine nx pi by L into x sine ny pi by L into y sine nz pi by L into z. So this is a standard result, we all know this. So we have to find the exact energies. So let us write this as exact. So exact energies and wave function of the ground state and fast excited state. So let us proceed. So we know that ground state is not degenerate. So and for ground, because for ground state we have nx, ny, nz, all of them to be 1. So exact ground state energy is given by the following: pi square h cut square by 2m L square, and we have here 1 plus 1 plus 1 squared. So this is basically 3 pi square h cut square by 2m L squared. And what will be the corresponding wave function? So our wave function will be phi 1 1 1, and we have here xyz. So this is root under 8 by L cube sine pi x by L sine pi y by L sine pi z by L. So this is our corresponding wave function. Now we have to calculate the fast excited state. So for fast excited state we have three possibilities. Nx can be 2 and ny nz can be 1, or we can have ny to be 2 or nx ny to be 1, nx nz to be 1, and we have another possibility where nz is 2 and nx ny can be 1. Why? Because for all these three quantum numbers, if we notice our energy value carefully, they will be same, because this nx squared plus ny squared plus nz squared, this term is same for all this, same for these three pairs. So our first excited state is threefold degenerate, and what is this corresponding exact energy value? So it can be 112, it can be 121, and it can be 211. So all of them corresponding to the same value. And what will be this value? So 2 squared plus 1 squared plus 1 squared. So basically it will be 6. So this value will be 3 pi squared h cut squared by ml squared. So this is our energy value. And what are the wave functions? So wave function, we have three wave function corresponding to the energy value. So one is 112. So it will be root under 8 by L cube sine pi x by L sine pi y by L sine 2 pi z by L. So this is one. What will be the second one? It will be 121. So for that, the wave function will be 8 by L cube sine pi y by L pi x. So let us write this. Pi x by L sine 2 pi y by L sine pi z by L. And what will be the third one? The third one will be 211. And what will be the corresponding eigenfunction? The eigenfunction will be sine 2 pi x by L sine pi y by L sine pi z by L. So these three wave function have the same energy value, which is this. So our first excited state is threefold degenerate. And now we have to find the using first order perturbation theory to calculate the energy of the first excited state. So let us proceed. So so to calculate the energy of the first excited state to the first order, we need to use degenerate perturbation theory, because this first excited state is threefold degenerate. So for that we need to find the matrix, the following matrix. So what we have done for the previous problem. So V11, V12, V13. So this is the matrix which we have to find out, and we have to find its eigenvalue. So what are the elements? So basically here this V they are defined as, so we have our definition like VNM. So that is basically N, our perturbative Hamiltonian, and M. So what is our perturbative Hamiltonian? So our perturbative Hamiltonian is this. So let us copy that. So let us just recall this and write down. So delta x, yeah. So our perturbative Hamiltonian is this. V0 L cube delta x minus L by 4 delta y minus 3L by 4 and delta z minus L by 4. So this is our perturbative Hamiltonian. So let us proceed and calculate the matrix element. So first let us calculate V11. So what will be V11? So v11, we can write down this will be our, so we, for shorthand notation, we will denote this phi 1 1 2. This we write down as 3. Phi 1 2 1, this will write down as 2, and phi 2 1 1, this we will write as 1. So what will be our v11? V11 will be 8v0 0 to L delta x minus L by 4 delta y minus 3L by 4 delta z minus L by 4 and here we will have sine square 2 pi by Lx sine square pi y by L and sine square pi z by L into here we will have dx dy dz, and all of the limit is from 0 to L. So we can calculate this. So basically we will have 8v0. So first we will put our x limit. So delta x minus L by 4 sine square 2 pi by Lx dx, y we have 0 to L delta y minus 3L by 4 sine square pi y by L dy, and z we have 0 to L delta z minus L by 4 multiplied with sine square pi z by L dz. So if we evaluate this, it will be 8v0 sine square pi by 2 sine square 3 pi by 4 sine square pi by 4. So this will give us 2v0. Similarly, so let us calculate a few more terms. So v12, so it will be 8v0 0 to L delta x minus L by 4 sine 2 pi by L x sine, so this is a cross term, so we will have two different one, dx 0 to L we have delta y minus 3L by 4 sine pi y by L into sine 2 pi y by L dy, and z integration we have 0 to L delta z minus L by 4 and sine square pi z by L dz. So this will give us 8v0. So this will give us sine pi by 2, and here we have sine pi by 4 multiplied with, here we will have sine 3 pi by 4 sine 2 pi by L into 3L by 4. So it will be basically 3 pi by 2, and another we will have sine square pi by 4. So this, if I evaluate, so this value will be minus 2v0. In the similar manner, let us calculate just one more term, v13. So it will be 8v0 0 to L delta x minus L by 4 sine 2 pi by Lx sine pi x by L dx. Then we have y limit, y is from 0 to L, it will be delta y minus 3L by 4, and here we have sine square pi y by L dy, and we have the last term about z, so it is delta z minus L by 4, and here we have sine pi z by L sine 2 pi z by L, so it will be dz. Yeah, so if we calculate, this will give us 2v0. So by this following manner we can calculate all the terms like v21, v22, v23 and v32 V31 and V33. So in the similar procedure we can calculate all of this. So if we calculate this, then we will get the following matrix. So our matrix will be 2V0. We will have 1 minus 1 1 minus 1 1 minus 1 and 1 minus 1 1. So what will be the so now we have to find the eigenvalue of this matrix. So let us proceed. So if lambda is the eigenvalue, then we will have the following characteristics equation. So 1 minus 1 lambda 1 minus 1 1 minus lambda, and here we have 1 minus lambda. So we have to solve this. So let us proceed. So 1 minus lambda, and here we have 1 minus lambda squared minus 1, and for the second term we will have minus 1 multiplied with 1 minus lambda plus 1, and third term we will have plus 1. Here we have 1 minus 1 plus lambda. So this is our equation. So from the first one we will get 1 minus lambda, and here we have 1 plus lambda square minus 2 lambda minus 1, and from the second term we are getting so minus 1, this will be plus lambda and plus 1, and here we have plus lambda. So we are left with 1 minus lambda multiplied with lambda, and here we are getting lambda minus 2, and here we have minus lambda plus lambda. So these two will cancel out. So lambda is 0 1 2. So this is our corresponding values. So if this is our corresponding eigenvalue, then our energy correction like our energy values, since our energy values is 3 pi square h cut square by ml square. So then our corrected values, so let us denote all of them so one value will be plus lambda 0 into, outside the matrix we have 2v0, so one will be this. So one value will remain same, and the second energy value will be 3 pi square h cut square ml square minus 2v0, and third value will be 3 pi square h cut square by ml square minus, so this is plus and this is plus 4v0. So these are our non-degenerate energy eigenvalues, and using these eigenvalues we can calculate the corresponding eigenvector. That means we can calculate the our good linear combination of our eigenstate which corresponding to this degenerate energy eigenvalues. So that is it for today's video. So we will meet on our next lecture video. Thank you.